Good evening, everyone. I'm Shivani Dhok and I welcome you all for the week 10 tutorial for the course of Simulations of Communication System using MATLAB. So like every week, this week's tutorial will also be divided into two parts. The first part will be recap of week 10 content and the second part will be the questions which are related to the week 10 content. You can stop me at any point if you have any questions. Okay, so let's quickly start with the recap of week 10 content. Just a minute. Okay. Okay. So, yeah. So let's start with the recap of week 10 content. So week 10 content was majorly based on how do we decode the communication signals. And to do that, we looked at two different rules. The first one was map rule. So we didn't specifically mention that this particular rule is a map rule, but let me just write it properly. So this map rule, or which is the abbreviation of maximum a posteriori probability or a posterior probability so this particular rule, what it says is, so it says that my optimal m hat or my m hat, the decoded symbol m hat, will be equal to arg max over m of probability that you have transmitted the signal sm given you receive y. Okay, this particular probability is called as a posteriori probability. What do you mean by a posteriori? It means that we have received a signal y. So given we have received a signal y, what is the probability that sm was transmitted? So this rule says that select that particular m as your m hat, which will give me the highest a posteriori probability. Now this a posteriori probability we can write as using Bayes rule. So using Bayes rule, probability that Sm given y is equal to PDF of y given Sm was transmitted into probability that Sm was transmitted divided by PDF of y. Okay, this is by Bayes rule. So if I substitute this in this equation with whatever we have written here for map rule, what we get is, so if we substitute it, we get, therefore m hat will be equal to arg max of m into this value whatever we have obtained, that is f of y given sm into probability that sm was transmitted upon f of y. Now this f of y is common for all m, and this f of y is anyway independent of m. So this we can write as arg max of m f of y given sm into probability of sm. Okay. Now, if probability of sm is equal to 1 by m for all m, then m hat, so this probability will become 1 by m, and that is simply a constant, not a function of m, little m. So we can simply remove it. So what we get is arg max of m f of y given SM. And this probability or this PDF here is known as likelihood function. Okay, and therefore this rule is known as maximum likelihood rule. Okay, so this was map rule and this was ML rule. So let me write it again. So your map rule is m hat equal to argmax of m, probability that you have transmitted m given you have received y, and then you have your ML rule. This ML rule is m hat equal to argmax of m into f of y given SM being transmitted, and your map rule becomes, or this is equal, this equality if that is all symbols are equally likely or are equiprobable. Okay, so this is all about your map and ML rule. And another thing for Gaussian noise, so we specialized this ML rule for Gaussian noise, or let's say we have y equal to s plus w. So and if this w is your Gaussian noise, therefore for Gaussian noise ML rule specializes as follows. So this rule becomes m hat equal to argmin of m y minus sm square, and this is basically your minimum distance rule. Okay, so this is all about your map and ML rule. After that, we simulated this particular thing for different constellations. Sorry. Yeah, we simulated it for different constellation, and we analyzed the effect of noise variance and also the effect of number of constellation points. So we saw that if noise variance is increased, if noise variance is increased, then the constellation points or the constellation points which we received, the received signals are is very close and may be indistinguishable means we may have errors or erroneous decoding. Okay. And how do we analyze this particular thing? Or what do we say? Which metric do we use to assess whether the decoding was proper or not? That is probability of error. So what do we mean by probability of error? So it says that probability that we receive some another symbol, we receive Sm prime if Sm was transmitted for some Sm, and this is your probability of error. And if we use law of total probability, we can write it as summation over m equal to 1 to m. If we have m constellation points, probability that Sm is changed to Sm prime for some m prime not equal to m into probability that Sm was transmitted. Okay, this is your probability of error, and this is the metric that we used. So we said that if my noise variance is increased, if noise variance is increased, probability of error increases. That is, we have more erroneous decoding, or we have lot of decoding errors. After that, we looked at the effect of number of constellation points, and this we looked at for two different cases. One for when the average energy of the constellation is fixed, and when the average energy of constellation is not fixed. So what we observed is, for this particular case, for MPSK, if m increases, the distance between two constellation points decreases, which means there are more chances of making errors while decoding. Which means if m increases, probability of error increases, and this is for your fixed. So if you're using same energy, anyway, if you add the number of constellation points in MPSK, fixed energy or no fixed energy doesn't matter. These 2 points matter. These 2 points matter when we have, or when symbols have different energies. Okay. So now this point I'll be writing for M Aripam. So here for fixed energy, sorry, for no fixed energy, if M is increased, we can increase average energy such that probability of error increases marginally. But this is not an appropriate comparison. The best comparison, or a better way to compare, is to compare it when we have fixed average energy. So this is more appropriate way to compare the results. And for this, for fixed energy or fixed average energy, if m is increased, then constellation points become closer again, and this increases the probability of error. Okay, so this we have seen through simulations also. We'll again see these things, and then we have this SNR, where this SNR is known as the signal to noise ratio. So this thing is signal to noise ratio. So this is signal power divided by noise power. And this is equal to, you can write it as E average upon N naught, where N naught is your noise power. Okay, is it clear? I hope this part is clear. After we saw that, the next thing that we looked at was a thing that is known as union bound. So I won't go into detail of this thing. So this union bound is basically a concept from probability. So it says that if I have probability of events, probability of union of events, this thing will be less than or equal to sum of m equal to 1 to n probability of individual events. Okay, this is the union bound, and when we apply this union bound in our case, we get probability of error as summation m equal to 1 to m summation m prime equal to 1 to m, where m prime is not equal to m, probability that Sm gets changed to Sm prime, or you detect Sm prime instead of Sm when Sm was transmitted, into probability that Sm was transmitted. And this thing here is known as pairwise error probability. Okay, so this we have seen in the lectures, and we had also specialized it for the case when this is equal to 1 by m. That is, all the symbols are equiprobable. After that, the last thing that we looked at was the average energy for different constellations, and we saw that average energy for m PAM comes out to be m square minus 1 by 6 into a. If I have the constellation points as plus minus a, plus minus 3a, and so on till plus minus m minus 1a. And for MPSK, this comes out to be equal to a if my constellation points lie on a circle of radius root a. And this is the constellation points that I have. Something like this. Okay, so this is all about the content that was covered in week 10. If you have any questions, then let me know. Otherwise, I'll move on to the questions part. Uh,
Excuse me, ma'am.
Sorry?
Excuse me, ma'am.
Yes,
Ma'am, in last year, ma'am, week 9, ma'am, in this question 7, it was like given which of the following represents the impulse response of a Hilbert transformer. But, ma'am, the actual answer was not given in options, ma'am. We have read in communication system that it is 1 upon pi t, ma'am.
correct.
But,
Huh.
ma'am, they were like given, all were given in complex terms, ma'am. So, ma'am, if possible, can you like discuss it in the end, ma'am? After these questions, you discuss.
Which assignment you are saying?
Ma'am, week 9, question 7.
Week 9, question 7. This year's week 9, question 7?
Yes, ma'am. Ma'am, this year, ma'am.
Okay, one minute. Let me open it. Just a minute. Let me open the assignment. Yeah, okay. Which of the following depends the impulse response of a Hilbert transformer? Uh, this looks weird. It shouldn't be a complex. Hilbert transformer is not a complex function. Can you do one thing?
Yes, ma'am.
Um, Put it in the forum
Okay, ma'am.
and
Okay,
ask
ma'am.
them for detailed answers. Why
Okay,
didn't
ma'am.
you attend today's session when Professor Ribu took it?
Uh, yes, ma'am.
There was one session by the professor today. Why didn't you attend that?
Ma'am, I attended ma'am, but I think around for 30 minutes, ma'am, there was silence, and I had uploaded my questions given in the Google form also, ma'am.
Okay.
So, yes, ma'am.
S-
Before that, but
So those were not discussed?
no, I think they were not discussed. I checked also the recordings also, ma'am. So I was like around half an hour in that YouTube session.
Okay, okay. So just do one thing. You put it in the forum and
Yes, ma'am.
it's looking weird, but let's see if I don't know why they haven't. Did they
Um,
release detailed solution?
no, ma'am. And also one thing, ma'am. The other TA, Anu Agarwal, ma'am. I asked her. So
Hmm,
she told me she checked actually. Na, it was that Lempel that question I asked you in last session,
huh,
I think.
hmm.
So she told me that that was the correct answer in last year's assignment, which was there in week 7, ma'am. So I think they were not given that assignment. So she did not discuss it after week 6 last year assignment. She directly discussed week 8 assignment. So but she checked on the last year assignment. The answer was actually Lempel-Ziv. This year they are putting sub band encoding, ma'am.
Just
So
a
which
minute,
one?
just a minute. Last year's assignment, which week?
Ma'am, week 7. You will find that, ma'am.
1 second, let me open. But the answer is not Lempel-Ziff for sure. If it is based on frequency, it is not Lempel-Ziff. It is subband coding. Again,
Okay,
you
ma'am.
put it in the forum.
Okay, ma'am.
And this week's which assignment? This was last week's assignment, right? In week 8's
Ma'am,
assignment, it
week
was
9,
there.
yes, ma'am. Ma'am, week 8 assignment, its solution has not been released yet, ma'am.
It is released.
It is released, ma'am.
Yeah, yeah. I'm able to see it.
But, ma'am, we have checked it, ma'am. In that week 9, the detailed solution. Yes, ma'am. For 9, I think. Yeah, 8, I think it is released, ma'am.
8, it is released. For 9, give them little bit time. Day before
Okay.
yesterday,
Yes,
the
ma'am.
deadline got over, right?
Yes, ma'am.
Just wait little bit. That's why I said you wait for the detailed assignment solutions to be released, and after that you put your
Okay, ma'am.
queries.
Okay, ma'am.
Still, that question was in assignment 8, right?
Yes,
Lempel-Ziff
ma'am.
one.
Last year it was, I think, in assignment 7.
I saw that, but it's not correct.
Okay, ma'am.
See, you open it and you can see the detailed solution, whatever is given.
Yes, ma'am. I can see that. And, ma'am, we had posted one more question that was, I think, related to step size. This was in actually week 7, that has not yet been re-evaluated, ma'am. We had posted it because it was not matching with the actual solution, ma'am. Week
Uh,
7, question 8, ma'am.
those things are not in my hand. You have posted it in the forum, they'll do it. You have seen they
Okay,
do the reevaluation. Give
okay,
them
ma'am.
little bit time, they'll do it.
Okay, ma'am.
Yeah, they have been doing the reevaluations. Just give them time,
Okay, ma'am.
because that is done by the NPTEL team, right? They have many
Okay.
courses to handle. They'll do it.
Yes, ma'am.
Don't worry.
Okay, ma'am.
Yeah. Any other thing?
No, ma'am.
Okay, but yeah, the answer is subband coding only. It is not Lempel-Ziff.
Okay, ma'am.
Yeah. Okay, if there are no further questions, I'll start with question 1 of today. So question 1 says that if a set of finite energy signals is projected onto an orthonormal signal space, the inner product of its constituents dash be preserved, and options are will be or will not be. Okay, so now what it says is, so let's say we have two signals, xt and yt. Both of them are finite energy. Both of them are finite energy signals, and then okay, and it says that we can project it onto orthonormal signal space. So let's say psi n of t for n equal to 1 to capital N with the basis of orthonormal signals, or it is orthonormal basis of the signal space. This is orthonormal. Okay, so you can write this xt as summation n equal to 1 to capital N xn into psi nt, and we can write this y of t as summation n equal to 1 to capital N yn into psi n of t. Now inner product of these finite energy signals is given by, so let me write it properly. Inner product of x of t and y of t is given by integral minus infinity to infinity xt into y conjugate of t dt. And let's say I have this vector x, which is x1 and so on till xn, and y as y1 so on till yn. Then inner product of, so let's say this is I1, of vectors x and y is given by summation n equal to 1 to n xn yn conjugate. Now the question is, let's say this is I2. Question is I1 equal to I2? That's all we need to figure out. If I1 equal to I2, then it will be preserved, otherwise it will not be preserved. So let's start with finding I1. So this I1 is equal to integral minus infinity to infinity xt into y conjugate of t dt. And then we can substitute this xt as whatever we have written here, and yt as things here. So this becomes integral minus infinity to infinity xt is summation n equal to 1 to capital N xn psi of t into yn conjugate, that will be summation m equal to 1 to n ym psi mt conjugate dt. Okay, now we can write this as integral minus infinity to infinity summation n equal to 1 to capital N summation m equal to 1 to capital n xn by m conjugate psi nt into psi m conjugate of t dt. Okay. Now what we can do, we can change the order or interchange the order of this summation and this integral, so we can interchange them. So what we will get is integral minus infinity to what we will get is summation n equal to 1 to capital N summation m equal to 1 to capital N. This xn and ym are anyway constant, they are not a function of time. We can take it outside. So this is xn into ym conjugate integral minus infinity to infinity psi n of t into psi m conjugate of t dt. Now this integral here will be equal to 1 if n is equal to m, is equal to 0 if n is not equal to m. So therefore we can write this as delta n minus n. Okay. So therefore we can write this as summation n equal to 1 to capital N summation m equal to 1 to capital N xn ym conjugate into delta n minus n. Okay. So this we can write as summation m equal to 1 to n summation n equal to 1 to n xn xm ym conjugate into delta n minus m. Now xm into ym conjugate are not a function of n, so I can just interchange it a little bit, something like this. And this is summation of impulses, and this n minus m cannot go beyond n. So this thing will be equal to 1. So therefore, this reduces to summation m equal to 1 to n xm into ym conjugate, where this thing is exactly equal to your I2, which is inner product of x, vector x and vector y. So this thing is equal to your I2, which means that the inner product will be preserved. Okay. So the correct answer is will be preserved. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. So the next question says, find the average energy of the following constellation. So this is the first part. So let's go part by part. So we need to find the average energy of this constellation. How does this constellation look? And we'll consider equally likely or equiprobable symbols. So this constellation looks something like this. This is A. Let's do it in this way. So this point is A. This is minus A. This is A. This is again minus A. And the 4 constellation points are here, 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 and here. So these points are minus A, A, minus A, minus A, A minus A, and A comma A. So these are the 4 constellation points that we have. And in last lecture also we have seen that this average energy or E average is given by summation m equal to 1 to capital M, where capital M is the number of constellation points, into probability of Sm, the probability of mth constellation point, multiplied by norm of Sm square. Okay, so now let's do that. So we have probability of Sm is equally likely, so this will be 1 by 4 summation m equal to 1 to 4 magnitude of Sm square. So this becomes 1 by 4. What is the energy of this? This will be A square plus A square plus the second point here. It will be again A square plus A square. Then third point here again it will be A square plus A square plus this point. Again it will be A square plus A square. So this becomes 1 by 4 into 8A square, which becomes 2A square. So therefore, average energy comes out to be equal to 2A square. Okay, so this is the average energy that we have. Now let us look at the second part of this question. It says that find the value of A if the average energy is given by E average. We have obtained E average equal to 2A. So what we have is, we have E average is equal to 2A square, and we need to figure out what is the value of A square. Now what is the value of A? So therefore this A square comes out to be equal to E average divided by 2, which means that A is equal to under root of E average by 2. Okay, so this is the first part, and then we have the second, this is the second part, and then we have the third part. We have to specialize the answer when E average equal to 1. So therefore if E average equal to 1, it implies that A comes out to be equal to 1 by root 1 by under root of 1 by 2, or this is simply under root 1 by under root. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the third question then. So this third question is basically construction of ML rule for different cases. So this says that consider two equiprobable messages S1 and S2, and so these are the two messages that we will be sending, S1 and S2, and the channel adds IID noise components, that is N1 and N2 to it. Okay, so basically we have S1 and S2 vectors here. So what happens is we have Y equal to Sm plus N bar. So this we can write in a vector form, that is Y11 or Y1, Y2, which is equal to Sm1, Sm2 plus N1, N2. Okay, and so what we have is, if S1 was transmitted, then Y1, Y2 vector will be equal to N1, N2. Okay, which means f of Y1, Y2 given S1 was transmitted will be equal to simply P of Y1 into P of Y2, which is PDF of N, for Y1, Y2 greater than or equal to 0. So therefore f of Y1, Y2 given S1 was transmitted comes out to be equal to e power minus Y1 plus Y2 for Y1, Y2 greater than or equal to 0. So how does it look? So we have this Y1, this is your 0, 0, this is Y1, this is Y2, and in this region it will be non-zero. Okay, so this is the non-zero region for Here f of y1, y2 given s1 was transmitted. Now, next part is if s2 was transmitted. So therefore, if s2, which is 1, 1, was transmitted, then y1, y2 will be equal to 1, 1 plus n1, n2. So therefore, I can write it as n1, n2 equal to y1 minus 1 and y2 minus 1. So therefore, by transformation of random variables, what we have is, therefore, PDF of y1, y2 given s2 was transmitted will be equal to p of y1 minus 1 into p of y2 minus 1. Simple. This is p of, and this will be true when y1 minus 1 and y2 minus 1 is greater than or equal to 0. That is y1, y2 will both are greater than or equal to 1. So therefore, f of y1 comma y2 given s2 being transmitted comes out to be equal to e power minus y1 minus 1 into e power minus y2 minus 1 y1 comma y2 both greater than or equal to 1. This we can simplify as e power minus y1 plus y2 into e power 2 y1 comma y2 greater than or equal to 1. Okay, and how does this look? This looks something like this. This is your y1, this is your y2, and then we will have 1 here and 1 here, and both y1 and y2 should be greater than 1. So it will be only in this particular region, like this. So this will be in this region. Okay, now what we need to do, we need to take ML rule. So what does ML rule say? ML rule, it says that m hat equal to argmax of m given y1, y2 given sm being transmitted. Okay, so what does this mean? So if f of y1 comma y2 given s1 is greater than f of y1 comma y2 given s2, then you decide in favor of s1, and if it is less than, then you decide in favor of s2. Okay. So this is what we are having. So what does it say? It says 2 points. 1, if f of y1 comma y2 given s1 is greater than f of y1 comma y2 given s2, then your m hat is equal to 1. If f of y1 comma y2 given s1 is less than f of y1 comma y2 given s2, which implies you decide in favor of m2, and you can put equality anywhere, either in the first part or the second part. So let's put it here. Okay, so these are the two things that we have, and now we need to compare these two PDFs. Okay, so now let us again go back to these diagrams here. This is y1, this is y2, this is 1. Okay, something like this. So this particular region which I have shaded with blue is for this one, that is f of y1 y2 given s1, and this particular region that is for y1 and y2 greater than 1. In this region, when both y1 and y2 are greater than or equal to 1, both f of y1 y2 given s1 and f of y1 y2 given s2 exist. So in this region, when we are in this region, you decide, since your f of y1 y2 given s2 is 0, decide in favor of, or decide m hat equal to 1. And now we need to figure out what happens in the overlapping region. So what we have for y1 y2 less than 1, m hat equal to 1, and now for y1 y2 greater than or equal to 1, we have an overlap, and therefore we'll use this equation. Okay, this equation we'll use. What was this? This was e power minus y1 plus y2, and this was e power minus y1 plus y2 into e square. This gets cancelled. We have 1 e square. And we know that this e square, this is greater than 1 always. Which means that for y1, y2 greater than or equal to 1, decide in favor of 2. So what we have is something like this. Let me draw that figure again. This is y2, this is y1, this is 1, this is the region for, so this is f of y1 y2 given s1, and then we have this, f of y1 y2 given s2, in this region decide m hat equal to 1, and in this region decide m hat equal to 2. So this is your ML rule. 1 minute. I think I have made some mistake here. small mistake I have made. So actually, so this is the region where your both y1 and y2 will be more than 1, and this is the region where anything can happen. Yeah, small mistake. So here you decide m hat equal to 1, and here you decide m hat equal to 2. Okay, so what mistake I made here is it's not this region. So both y1 and y2 should be greater than or equal to 1. So if you observe this region, your y1 is less than 1, but y2 is more than 1. Similarly, in this region, your y1 is less than 1 and y2 is more than 1. So we need to look at only this region. My apologies, I made a mistake here. So it is this region. So let me again write it. So this we are having. So this is y1 equal to 1, this is y2 equal to 1. So this is y2 equal to 1, this is y1 equal to 1. And this is the region of our interest for, this is the region for f of y1, y2 minus 1. And this is the region of y1, y2 given s2. So in this region, you decide m hat equal to 1, and in this region, you decide m hat equal to 2. So mathematically, your ML rule becomes m hat equal to 1 if y1 less than or equal to 1, or let's say less than 1, or y2 less than 1. It is equal to 2 if y1 greater than or equal to 1 and y2 greater than or equal to 1. So this is your ML rule. Okay. If there are any questions, then let me know. Otherwise, I'll move on to the next question. Okay, so the next question says that repeat the previous question if n1 and n2 are IID Gaussian with zero mean and unit variance. So what it says is here n1 and n2 both are distributed as zero mean Gaussian with unit variance, and they are IID. That is, they are independent and identically distributed. Okay. So again, we will first figure out what is f of y given s1. So your for s1, your y will be equal to simply your n1 n2, or let me write it in more proper fashion, f of y1 y2 given s1. So this will be equal to your where your p of n is equal to 1 upon under root 2 pi e power minus n square by 2. Okay, so this now becomes, sorry, p of y1, p of y2. So now this becomes 1 over 2 pi into e power minus y1 square by 2 into 1 over 2 pi into e power minus y2 square by 2. So this simplifies as 1 over 2 pi into e power minus y1 square plus y2 square by 2. Now similarly, if we have f of y1 comma y2 given as 2, it will be equal to, so we'll have y equal to 1 1 plus n1 n2. So now this will become p of y1 minus 1 into p of y2 minus 1. Okay. So this becomes 1 upon under root 2 pi into e power minus y1 minus 1 square by 2 into 1 upon 2 pi into e power minus y2 minus 1 square by 2. So this becomes 1 over 2 pi into e power minus y1 minus 1 square plus y2 minus 1 square by 2. We can simplify this as 1 over 2 pi into e power minus y1 square minus 2y1 plus 1 plus y2 square minus 2y2 plus 1 divided by 2. So this becomes 1 over 2 pi into e power minus y1 square plus y2 square, these two I can take common, by 2 into e power minus, or let's say plus 2 times y1 plus y2 minus 1 by, so these two gets cancelled. Let me keep it like that only. So what remains is 1 over 2 pi into e power minus y1 square plus y2 square by 2 into e power y1 plus y2 minus 1. So this is what we are having right now, and this is the second one. Now again we need to apply ML rule, and we had derived our ML rule, which is something like this. So let me just copy paste it. So this is the ML rule that we are having. Now this f of y1, y2 given s1 came out to be equal to 1 over 2 pi into e power minus y1 square plus y2 square by 2. This will, if it is greater than s1, if it is less than s2, and this came out to be equal to 1 over 2 pi into e power minus y1 square plus y2 square by 2 into e power y1 plus y2 minus 1. This gets cancelled. This also gets cancelled. So what we have is 1 if it is greater than s1, if it is less than s2, of what? E power y1 plus y2 minus 1. I'll do a small thing. I'll just change the LHS to RHS, something like this. So we have e power y1 plus y2 minus 1. If it is greater, then I'll have s2. And if it is less, then I'll have s1. So if this thing is greater than 1, we'll decide in favor of s2. And if this quantity here is less than 1, then we'll decide in favor of s1. Same thing I have written. If this thing is greater than 1, then we will decide in favor of s2. And if this thing is less than 1, then we'll decide in favor of s1. Now this is, we can take log, and log is monotonically increasing function. So if I take log on both the sides, natural log on both the sides, nothing will change. But we will get natural log of e power y1 plus y2 minus 1 greater than or equal to, or log 1 is 0. So therefore now this reduces to y1 plus y2 minus 1 if it is greater than s2, if it is less than s1. So therefore y1 plus y2, so this is the final decision rule. So this thing here is the final ML rule. Is it clear? Any questions? Okay, if there are no further questions, then let me move on to the next question then. So now we have derived ML rule for M point constellation in AWGN. Show that it is minimum distance rule. What happens if all the symbols have equal energy? So this is what is being asked to us. So first thing we need to do is we need to derive ML estimate ML rule for M point constellation and show that it is the minimum distance rule. Okay, so it is for a AWGN channel. So the maximum likelihood ratio rule maximum likelihood rule is M hat equal to argmax of M f of y given Sm. So this is the maximum likelihood ratio rule, and we have seen that for AWGN noise or for AWGN, f of y bar given Sm is 1 upon pi n naught to e power minus to the power n into e power minus norm of y minus Sm square by naught. Okay, so therefore M hat is equal to argmax of M 1 upon pi n naught to the power n into e power minus y minus Sm square by n naught. Now in this is constant and common for all, which means we can ignore. So this is equal to argmax n e power minus y minus Sm square by n naught. Now what we can do is take natural log, and since natural log is monotonically increasing function, this max thing is preserved, so it will still remain max. So this becomes argmax of M minus y minus Sm square by n naught. Now here, now what we will do is minus 1 by n naught is less than 0. It's a negative quantity. So if we remove that, max will get converted to min. So it's like this. If I have a function and I want to find a max of this, which is this value, and if I multiply it by minus sign, it becomes like this. So now the maxima becomes the minimum. So therefore, if I remove this negative quantity, or in short, if I multiply it by minus sign to this, what I get is R min of M y minus Sm square. So this thing here is Euclidean norm or L2 norm, which is distance between y bar and Sm, vector y bar and Sm, which means that M hat is M such that distance between y bar and Sm is the lowest. Which means ML rule is equivalent to minimum distance. Okay, so now we have done the first part, that is we derived the ML rule for M point constellation in AWGN, and now we have also showed that it is the minimum distance rule. Next thing that we need to show is what happens if all the symbols have equal energy. What does it mean? So this second part means that norm of Sm square is some E, which is independent of your M. Okay, so let us try to simplify it. So what we had is M hat equal to argmin of M, like this. We can simplify this norm as norm square plus norm of Sm square minus 2 times inner product of y and Sm, or to be very precise, this will be 2 times real part of inner product of y and Sm, and now this is argmin over M, like this. Again, this thing is constant, so this becomes argmin of M. You can take out minus sign common, or I can multiply by minus sign and make it as argmax. So I'm multiplying it, so this will be equal to 2 times real part of inner product of y and Sm minus norm of Sm square. And what is given to us is this quantity is equal to E, and it is constant. Okay, so therefore this becomes argmax of M to real part of, and 2 is also constant, we can ignore them, so this will be real part of y, inner product of y and Sm. So this thing here is correlation of y bar and Sm bar. So when we have constant energy for all the symbols, what we can do is we can simply project the received vector on all the SMs and then figure out what we and whichever is giving me the biggest value, that will be equal to my, that M will give me my decoded symbol. So this part also we have done. If you have any questions, let me know. Otherwise, I'll move on to the next question. Okay, so let me move on to the next question. So it says that specialize the results in question 5 for binary panel. So binary pulse amplitude modulation, what does it mean? Binary means M equal to 2, which means, let's say E is the average energy, which means the constellation is minus root E and root E. So the constellation point or the constellation looks something like this. Okay, these are the two constellation points that we will be transmitting. Okay, So now we need to specialize the results that we have in the previous question. So what was the result that we obtained? So this is the result that we have obtained here, argmin of y minus sm. So let's say this is s1 and this is s2. So m hat, or let's say sm hat, is equal to argmax of s belonging to plus minus root e. Here your y is, so your y will be equal to sm plus n. So your L2 norm square is simply your y minus s square. And this s can take value from plus e or minus e. So therefore, so not max, min. So what we have is, if y minus root e is greater than y plus root e, then my sm hat will be equal to minus root e. And if y minus root e is less than y plus root e, and we can put squares also, then sm hat will be equal to root e. Okay, so we can write this in a more concise fashion like in the previous questions. So if y minus root e square, if it is greater than y plus root e square, then decide in favor of minus root e, otherwise decide in favor of. Okay, so now we can simplify this. So these are anyway real values. This mod is equal to simple square. So we can write it as y square minus 2 root e y plus e greater than or equal to minus root e, like this. This will be y square plus 2 root e y plus e. These get cancelled. These are common. So therefore what we have is, we can take this thing this side. So therefore we will have 4 root e y. If it is greater than 0, then decide in favor of root e. If it is less than 0, then decide in favor of minus root e. Now 4 root e is common, so this y I can simply multiply by 1 by 4 root e on both the sides. So if y is greater than 0, decide in favor of root e. If y is less than 0, then decide in favor of minus root e. Okay, so this is what we have here. So what does it mean? So now if what we have is, let us try to understand what exactly is happening. Okay, so this is 0. This is the decision threshold that we are having. So what is happening is, in this region, let's say I have root e here. So in this region, decide in favor of root e, and in this region, decide in favor of minus root e. And this is your minus root e. And this is your maximum likelihood ratio, maximum likelihood rule. So what does it mean? We have something like this. So this thing here is your f of y given root e being transmitted, which is 1 over 2 pi n naught into e power minus y minus root e square by 2 n naught. Let's see what I have taken. Yeah, 2 n naught. And similarly, I'll have something like this. So in this particular decision region, or in this particular region, you have, okay, so this curve, whatever I have drawn, is your y, this one, which is equal to 1 upon 2 pi n naught into e power minus y plus root e by 2 n naught. So this we have. So in this region, if you observe the likelihood function when, or the conditional PDF of y given root e being transmitted is higher than the PDF of y given minus root e being transmitted. So your likelihood ratio, likelihood rule, maximum likelihood rule slowly translates to this particular rule. Okay, this is the exact same thing. Any questions? Okay, if there are no questions, then let me move on to the next. Now it says that find the error probability of, find the probability of error for binary PAM. So what we know about binary PAM from this question is the decision rule. So it says that from previous question, the decision rule is y, if it is greater than 0, then decide in favor of root e. If it is less than 0, decide in favor of minus root e. And this is the decision rule or decision regions that we have obtained. Okay, so this is the decision rule. So what is the probability of error? Probability of error is probability that root e gets converted to minus root e given root e was transmitted, that is, plus probability that, okay, let me write it properly, given root e was transmitted into probability that root e was transmitted plus probability that minus root e gets converted to root e given minus root e was transmitted into probability of minus root e. Since the symbols are equiprobable, this is half of probability that root e gets converted to minus root e given root e was transmitted less probability that minus root e gets converted to root e given minus root e was transmitted. Okay. Now if you observe here, if root e was transmitted, this is the conditional PDF, but you received minus root e. So whatever tail you are having here, this will lead to your uh, error. And similarly, whatever tail we are getting here, it is in the decision. So we have transmitted minus root e, but now we are obtaining root e. Okay, so now since this plot is symmetric, these two values are equal. Just a homework, try to figure out both the values and show that those are equal. Due to symmetricity, both are equal. So this is simply equal to root e getting converted to minus root e given root e was transmitted. So what it says is, this is probability of, and so we'll integrate the conditional probability of y given root e was transmitted in that region where you detect minus root e. And where do you detect minus root e? You detect minus root e from minus infinity to 0 in this region. So you detect it from minus infinity to 0 dy. So this region of detecting minus root e. Okay, so this is how you found find the probability of error. So this comes out to be equal to integral minus infinity to 0. What is the this probability? This is 1 upon under root 2 pi n naught into e power minus y minus root e divided by 2 n naught. Okay, and this comes out to be equal to q of under root of e by n naught, and where q of x is equal to 1 over 2 pi integral minus infinity to x e power minus t square by 2 dt. Okay, so this is the probability of error that we have obtained. Sorry, something is wrong. Wait a minute. This q of x is 1 over 2 pi into e integral under root 2 pi integral x to infinity. So this is basically probability that your x is greater than x. This is tail probability x to infinity e power minus t square by 2 dt. So this is equal to basically q of x minus, so it is q of 1 minus q of mean is root e by under root n naught, and your x is 0. So this is 1 minus q of minus under root e by n naught, and this is equal to q of under root e by n naught. So we are also using this fact that 1 upon q of minus x is equal to q of x. Okay, so this is what we are getting. So therefore, probability of error for binary PAM comes out to be equal to q of under root e by n naught. Is it clear? Any questions? Okay, if there are no questions, then we'll move to some coding questions. These questions were done, or this coding part was done in the lectures, but still I want to do it again from the scratch to understand the things better. So what we'll do 3 questions. First question, what we will do is we'll write a code to simulate symbol error probability for MPAM, memory PAM. After that, what we will do, we have uh, we have derived the probability of error for memory PAM for m equal to 2. So what we will do, we have this analytical expression, and that we will try to match with the simulation. Okay, that will be our question 9. And in the last question, what we will do, we will write a code to simulate the symbol error probability for memory PSK. So what I'll do, I'll now shift to MATLAB, and one by one we'll solve these 3 questions. And along with these files, I'll also upload the MATLAB files for these 3 questions. Okay, so let me stop sharing here. Okay. So let me share my MATLAB screen. Okay, so let's start with the question 9. me close all the other codes also. Okay, so let's do this code for question 8, Emery Pam, singular probability or probability of error. And what does this code does? This code will plot symbol error probability or probability of error for Emery pulse amplitude modulation. Okay. So now when we are writing codes for communications, what we will do is we'll do step by step. So the first step here is to set up simulation parameters. Then get constellation points. Then once we have these constellation points, what we will do is then, okay, let's do these two things first. So for simulation parameters, what we will do first thing is this is number of realizations of noise and symbols. So how many random symbols you want to generate? Then we have M. Let's start with 4. So this is basically your number of constellation points. Then we have N naught, which is equal to, let's say, 1 for now. So this is your noise variance. And then let's have E average. And let's take it from 0 to 21. Let's say we have 0 to 10, and let's say we have 21 points. Average energy. This is all in linear scale. Okay, once we have these things, next thing we'll do is we'll get our constellation points. So for now, let's say not normalized by E average. We need to do it, but we'll do it afterwards. So this is what we are having, and the constellation points, let's say, is this is Emery Pam. So this is minus of M minus 1 to, let us run these things first. Once we run this, what we have is N as 10 raised to 6, we have M as 4, N naught as 1, then E average as lot of values, and then we have N naught as 1, and we have our constellation matrix as minus 3 1 1. So this is what we wanted. Minus 4 is minus 4 minus 1 is 3, so minus 3, then space by 2, and again 3. Okay, so we have reached till this point, and now what we will do, for each of this average energy, we'll transmit the signal. So the next part is get the simulation for all the values of average energy. Okay, so for II equal to 1 to length of what, how, for all values of average energy, so length of E average. So this II will be from 1 to 21. Okay, we need to run something. So what we need to do first? First we need to get normalized constellation points, and for that we'll use the E average definition that we have obtained, and that we get, so that will help us to get the minimum distance between 2 points, and the d min came out to be equal to square root of 12. You check your notes, it comes out to be, so this E average is equal to d mean square into m square minus 1 upon 12. So that is what the E average is. So when we simplify it, it comes out something like this: II divided by m square minus 1. So this is the d min, that is 12 into E average for that particular iteration divided by m square minus 1, and then your constellation will be simply A multiplied by 0.5 into d min. So this d min is basically between 2 points, so we need to divide it by 0.5. So this is what we are getting. Now next what we need to do is get n random constellation points for transmission. Okay, so for that we'll take our standard trick. So index rand I. So these will be between 1 and m, and how many do we want? N comma 1. So this will give n random indices between 1 to m, and then we will get our SM, that will be a constellation of index. So get random symbols to be transmitted. After that, add noise to the transmitted symbol. Okay, so for that my noise will be equal to square root of n naught multiplied by rand n comma 1, and then my y will be equal to sm plus n. So this thing here is basically AWGN noise with zero mean and variance n naught, and this thing here is received signal. Okay, so what I'll do, I'll run it for one time and then you can see what happens. Okay, so I have ran this particular code for one iteration. I have added a breakpoint, and for II equal to 1 I have done. So I get a noise, Gaussian noise. So if I plot histogram, of this. So it is a Gaussian noise. You can see that it is a Gaussian noise. And I have this SM. So this SM is basically, oh, what happened? Wait a minute. Something is wrong. Why is demon coming as? Oh, okay. Let me do it. Some error came up, I think. So. Okay, we need to be very careful. This SM becomes some different dimension. To be very careful. So all of these should be of 10 raised to 6. Yeah, okay. So this is a constant, something like this. We have, and this daemon comes out something like this. So if I see this SM is something. So if I plot, so you have 4 points coming like this. That is something like this here. And your A constellation is something like this. Now we have YM, and next thing that we need to do is, so this is the received signal. We now have the received signal. Now we need to do ML decoding. That is minimum distance decoding. Okay. So now I'll show you a trick. Instead of using a for loop, what we can do is, let's say I have A as 1, 2, 3, 4, like this. And let's say I have some M as 1, 2, 3. And what I want to do is, I want to find difference between one with each entry of this A vector with each entry of this M vector. So what I can do is, I'll simply do A minus M. Oh, sorry. This will be 1, 2, and 3. So I'll do A minus M. So now what happens is, my A was 1, 2, 3, 4, and again my M was 1, 2, 3. So this is 1 minus 1, 1 minus 2, 1 minus 3. 1 minus, 2 minus 1, 2 minus 2, 2 minus 3. So what is first row giving me? First row is giving me difference between 1 and all the entries of this particular thing. And similarly, second entry here, it gives me 2 minus all the entries of, so second entry of A minus all the 3 entries. Similarly, third entry, third row gives me 3 minus all of these values, and something like this. Now what is happening here is, I have this Y. This Y here is 10 raised to 6. Now if I use a for loop for each Y, it will take long time. So instead of that, what I'll do, what I want to do is, I want to find the distance between this Y and each of this constellation point. So I have this 4 constellation points. So what I'll do, I'll find out distance between Y and all the constellation points. Okay, and if I do that, what I'll get is something like this. So if you see this D all, this is the distance between the first point Is it same? Yeah. So if you see, this is the difference between my A constant and your Y absolute value. So if you take this minus this and absolute value, that will give me the first entry of this particular thing. Okay, so now what happens here is this D all. So first row of D all, first row contains the difference between the first entry of Y and all four constellation points. Now I need to select the index of 1, 2, 3, 4 such that this is the that gives me the minimum of them. So I want from this particular row, I want the minimum distance, which is 0.9335. Similarly, from second row, I want this particular value. So now what we will do is, okay, let me keep it here. Okay, so now what I'll do, I'll try to get the index after decoding, which is equal to, or let's say it will be very nice value, which will be equal to minimum of D all, but its transpose. Because min will give me column wise minimum, but I want row wise. So in order to do that, what we will do, we'll just take transpose of it. So now let me just add a breakpoint here. Okay, so now see, this is D all. This is the D all that I have, and this is the minimum value that we will get. So first entry is 0.7893. Is it giving? Ah, okay. Okay, just let me run it till 3. Yeah, okay. So this is val, then this is D all. So if you observe, this 0.1326 is the minimum value which is showing up here. And now if I see decoding index, that is equal to 3. So if you observe, this 0.1326, which is the minimum, is at this third location. So this is giving me the minimum distance is index. Okay. So that is okay, that we have verified. And now what we will do is, we'll take SM hat, or let's say decoded will be a constellation into index decoded. So this is the end of my decoding part, and now I need to do get probability of error, which is equal to number of errors divided by n. So number of errors will be equal to sum of double of SM not equal to SM decode, and probability of error for ith SNR comes out to be equal to number of errors divided by n. Okay, now if I run this error is coming. Again, same issue. This needs to be transposed. Okay, so this runs and I get probability of error PE just a minute. It's decoded. So let me do it in this fashion. N minus sum of IDX equal to IDX decoded transpose. If I do it, okay, some issue was there. I don't know why. Sum not equal to sum code transpose. Some issue is there. IDX minus IDX. Okay. So here I am just taking index, and if those indexes are not matching, then I am just taking an error. So this is what I'm having. Now once I have this probability of error, next what we will do, we'll plot it. Okay, so let's do that. So that is plot E average comma PE, or let's not do this, we'll do semi-log y. So what it will do, it will do y-axis in log scale, and x-axis will be in linear scale. Then we'll have x label as average energy and y label as probability of error, and let's do grid on. Okay, and if we do that, we get a plot which is something like this. And if we set at m equal to 2, we get a plot which is something like this. Now what we will do is, we'll take this up, we'll take this, so this is the probability of error or symbol error probability plot for m-array PAM. Now we'll take this up and do our question 9. So we'll do this for binary pulse amplitude modulation and match with analytical expression. So everything remains same, simulation part remains same. What we will do is, we'll just add another thing which is analytical, which is equal to or we obtained it as Q function of square root of E average IIth value divided by N naught. Okay, this is what we had obtained. Now what we will do, semi-log by E average comma PE analytical, then we will hold it on and we'll plot this with circles, and then we will do hold off, and now let us run this. And this is my question 9. Pam, sorry, binary pulse amplitude modulation SAD. Okay, so now if you observe here, let me add legends also. First plot is analytical and second is simulation. Okay. So if I run this, if you observe carefully, see the simulation plot is overlapping with the analytical plot. Okay, if it will be very difficult to see. Let me make line width as 2, line width as 2, and let me rerun. Yeah, so now if you see, spelling mistakes. Yeah. Okay, now if you see here, this blue line, this blue solid line is analytical, and this markers, this circles are simulation plots, and it is exactly overlapping, which means that the analytical equation that we derived is correct and the simulations that we are doing is also correct. Okay, now let's do it for some different value of n naught. Let's say I increase my decrease my n naught as 001. Okay, so, okay, let's not do this. Let me do it for n naught equal to 2. So this is how, so for all values of n naught it is working. Okay, so this is all about question 9, and now we'll move on. Any questions till this part for question 8 and question 9? Okay, I hope there are no questions. Now we will do the same thing for MPSK. So this is the question 10. We need to do it for MPSK. This is for question 10. And what changes? So everything will be same. So we need to do it for Emery phase shift keying. Everything remains same. So the simulation setup remains same. Nothing changes. What changes is constellation points. So this constellation point will change. So this will be e power minus j 2 into pi into 0 to m minus 1 divided by m. So this is the constellation without, so this is normal, this is not having any energy component. So now we want to get normalized energy coefficient. So this now will be equal to this constellation point into square root of E average. So this thing will change. Okay, so we have this constellation points, then so we have this constellation points, then we have the constellation scaled by energy, scaled by average energy, then we have something I did find here. Okay, then again I'll generate random indices for getting constellation points. Then I'll get the constellation points from this. Then I'll have this noise, but now this noise will be complex. So if you observe here, the noise should be a complex random variable plus 1i into rand n comma 1. But in order to keep the variance as n naught, I need to multiply it by square root of n naught by 2. Then I'll have y equal to sm minus this thing. Then I have this thing here, like this is the received signal. Then I have this d all, that is the minimum distance. So decoding and every remaining step remains exactly same, nothing changes. So now if I run this, I'll get some plot which is something like this. Now if I see my this y, if I plot it, so this is something like this. So if I may do it a little bit nicely, plot y comma, so this is your PSK constellation. Of course it is overlapped, so that's why it's coming something like this. Then we have our probability of error. We can increase this, make it for m equal to 16, and we get it really bad. What we can do is we'll do it for m equal to 4 and increase this to, let's say, 20. If we do that, we get it something like this. And now if I plot this y, it comes something like this. So it is well separated now because my energy is higher. So this is all about simulation and coding part for this week. I'll upload these questions in the I'll upload these codes also in the Google Drive along with the notes for today. If you have any questions, please let me know. This was all I wanted to cover today. If you have any questions, then please let me know. Otherwise, you're free to leave the meeting. Thank you for attending today's session.